We're going to study cosets again, but this time in the context of rings. But first, let's do a review of groups whose operation is addition. So, consider the additive group of integers, z, and its subgroup, 5z. Here are the opening questions. Part A, find all distinct cosets of 5z. Now note that since the operation here is addition, these cosets have the form a plus 5z, where a is an integer. Part B, find the smallest positive integer b such that the cosets 378 plus 5z is equal to b plus 5z. Then part C, find the coset sum 3 plus 5z plus 4 plus 5z. So if you could pause the video and work on these questions, and we'll go over them shortly. Recall that we've formed a quotient group z mod 5z, consisting of the cosets 0 plus 5z through 4 plus 5z under the operation of coset addition. Here are some essential properties of these cosets. First, cosets a plus 5z and b plus 5z are equal to each other if and only if the difference of their coset representatives, namely a minus b, is contained in 5z. For example, the coset 378 plus 5z is equal to 3 plus 5z because 378 minus 3, or 375, is contained in 5z. And using this property, all cosets in z mod 5z can be reduced to one of 0 plus 5z, 1 plus 5z, 2 plus 5z, 3 plus 5z, or 4 plus 5z. Now let's talk about how we add cosets. Note that we're adding these cosets here as opposed to multiplying them because the group operation of z is addition. Now recall that coset addition was a tedious process where we had to add every element of one coset to every element of the other coset. But fortunately, we found a shortcut where we can simply add the coset representatives. Thus, the coset sum a plus 5z plus b plus 5z is the coset a plus b plus 5z. And using this shortcut, we have the coset sum 3 plus 5z plus 4 plus 5z is 7 plus 5z, because 7 is 3 plus 4, and 7 plus 5z reduces to 2 plus 5z because the difference of the coset representatives, 7 minus 2, is 5, which is in 5z. And so that's the shortcut that we have for adding cosets. We've seen that the quotient group z mod 5z is isomorphic to z5 as additive groups. Here's the addition table for z mod 5z. For example, we just saw that 3 plus 5z plus 4 plus 5z is equal to 2 plus 5z. Now, this table looks just like the addition table for z5, especially if we ignore the plus 5z in each entry of the table. And that's how we know that z mod 5z is isomorphic to z5 as additive groups, because they have essentially the same addition table. But z5 is a ring where we can also multiply, not just add. So can we define multiplication in z mod 5z and turn it into a ring too? For instance, the coset product 3 plus 5z times 4 plus 5z. What should that equal? We'll answer this question in the next slide, but you might want to pause the video and think about it on your own first. And here's the answer. we adapt the shortcut for coset addition and apply it to coset multiplication. So to find 3 plus 5z times 4 plus 5z, we can simply multiply the coset representatives and obtain 12 plus 5z, which reduces to 2 plus 5z. So 3 plus 5z times 4 plus 5z is 2 plus 5z. And in general, we multiply cosets in z mod 5z using the following rule. A plus 5z times b plus 5z is the coset a times b plus 5z. Now, there is an important technicality underneath this definition in which ideals, such as 5z, play a role. But for that discussion, please read chapter 32 in the textbook. Here is another example of coset multiplication. 2 plus 5z times 3 plus 5z equals 6 plus 5z, which reduces to 1 plus 5z. Now, 1 plus 5z is the multiplicative identity of z mod 5z. And therefore, 2 plus 5z and 3 plus 5z, which multiply together to be 1 plus 5z, are multiplicative inverses of each other, and hence they are units. And we write 2 plus 5z to the minus first power. In other words, the multiplicative inverse of 2 plus 5z is equal to 3 plus 5z. And similarly, 3 plus 5z to the minus first power, in other words, the multiplicative inverse of 3 plus 5z is equal to 2 plus 5z. Thus, we conclude that z mod 5z is a quotient ring. In other words, a set of cosets where we can add and multiply. And moreover, z mod 5z is isomorphic to z5, not just as additive groups, but as rings. We're going to take this up a notch and work with quotient rings involving polynomials. Thus, consider the polynomial ring z3 bracket x, consisting of polynomials whose coefficients are in z3, and also the subset bracket x squared, the principal ideal generated by x squared, which is the set of all multiples of x squared. Now the quotient ring z3 bracket x mod bracket x squared contains cosets, additive cosets, of the form a of x plus bracket x squared, where a of x is a polynomial in z3 bracket x. Now, we can compare this with z mod 5z, which contains cosets of the form a plus 5z, where a is an integer. And in the quotient ring involving polynomials, bracket x squared will play the role of 5z in z mod 5z. Both of these are ideals, and moreover, 5z, which is the set of all multiples of 5, can be written as bracket 5, or the principal ideal generated by 5. And so the quotient ring, z3 bracket x mod the ideal generated by x squared, looks quite intimidating perhaps, but it is very similar in the way it works with z mod 5z, as you will see in the classwork. Now please pause the video and work on day 32 classwork. And afterwards, we will go over some of the problems and concepts. In problem 2 of today's classwork, we have two polynomials, alpha of x and beta of x, as shown. Now, these are unequal in z3 bracket x. In other words, they're different as polynomials because alpha of x has degree 7 and beta of x is a linear polynomial with degree 1. However, in the quotient ring, their cosets are the same. In other words, the coset alpha of x plus bracket x squared is equal to beta of x plus bracket x squared because the difference of the coset representatives, alpha of x minus beta of x, which is equal to this highlighted portion right there, that is a multiple of x squared, and hence it's contained in bracket x squared. So to summarize, even though the polynomials alpha of x and beta of x may be different, the cosets that they generate could still be the same. Now, this is very much analogous to how the integers 378 and 3 are different. So they were different in z. However, their cosets, 378 plus 5z and 3 plus 5z, those are equal to each other in the quotient ring because the difference of the coset representatives, 378 minus 3, is an element of 5z. And so this is very much the analog of what we saw with the polynomials. This example shows how each coset in the quotient ring can be reduced so that its coset representative is at most a linear polynomial, such as 2x plus 1. And therefore, in problem 4, we concluded that the distinct elements of the quotient ring are cosets of the following form, where the coset representative is at most a linear polynomial ax plus b, where the coefficients a and b are in Z3. Now, with 3 choices for the coefficient a, namely 0, 1, 2, and 3 choices for the coefficient b, we have 3 times 3, or 9 cosets in this quotient ring, as shown here. But one question remains: how do we know that these 9 cosets are actually distinct from each other? So for instance, how do we know that this coset, x plus 2 plus bracket x squared, and this one, 2x plus 1 plus bracket x squared, how do we know that those 2 cosets are actually different cosets? And for the answer to that question, please watch the proof of the day that appears later in this video. And now that we know its distinct elements, in the next couple of slides, we'll do some computations in this quotient ring. Let's try multiplying these 2 cosets, x plus 1 plus bracket x squared times 2x plus 1 plus bracket x squared. By the definition of coset multiplication, we can simply multiply the coset representatives, and so we obtain x plus 1 times 2x plus 1 plus bracket x squared. Now, expanding this polynomial product, we get the following: 2x squared plus x plus 2x, so that's 3x, plus 1 plus bracket x squared. But the coefficients of this polynomial is in Z3, and therefore the 3 here becomes 0. So we're left with 2x squared plus 1 plus bracket x squared. Now, how can we reduce this coset? Well, we claim that it's equal to 1 plus bracket x squared because the difference of the coset representatives, namely 2x squared plus 1 minus 1, is equal to 2x squared, which is a multiple of x squared, and therefore it's contained in bracket x squared. To summarize, these 2 cosets multiply together to 1 plus bracket x squared, which is the multiplicative identity of our quotient ring. And therefore, these 2 are multiplicative inverses of each other, and hence they are units in the quotient ring. here's another computation. Let's consider the coset x plus bracket x squared. Now, first of all, this does not equal the zero coset, namely 0 plus bracket x squared, because the coset representative x is not contained in bracket x squared. Now let's see what happens if I multiply this coset by itself. Well, if we multiply the coset representatives, x times x, we get x squared plus bracket x squared. And that is equal to 0 plus bracket x squared, because x squared is contained in bracket x squared. It's a multiple of x squared. This is very much analogous to saying 5 plus 5z is the same as the coset 0 plus 5z. To summarize, we have x plus bracket x squared, which is not the zero element of the quotient ring. When we multiply it by itself, we do obtain the zero element, namely 0 plus bracket x squared. And therefore, x plus bracket x squared is a zero divisor, and hence it is not a unit, because in a ring, an element cannot be both a zero divisor and a unit. And the existence of this x plus bracket x squared, which again is a non-zero element that is not a unit, from there we can conclude that our quotient ring is not a field. This is an important example because a key question in the remainder of this course is the following. When is or isn't a polynomial quotient ring a field? And this example is the first glimpse into that question. Let's return to problem 4, where we claimed that these 9 reduced cosets are distinct from each other. Now note that these coset representatives are of the form ax plus b with degree at most 1. So we're claiming, for example, that since x plus 2 does not equal 2x plus 1 as polynomials in Z3 bracket x, then their corresponding cosets are also different in the quotient ring. And the key here is that the difference of these coset representatives, that difference is not contained in bracket x squared. So we'll generalize this as a theorem and proof in the next slide. So here's the theorem. If the polynomials a1x plus a0 does not equal b1x plus b0 in Z3 bracket x, so think of this as, in our example, x plus 2 not equaling 2x plus 1 in Z3 bracket x. So if those two polynomials are different, then their corresponding cosets are also different in the quotient ring. That's what this theorem is stating. So as usual, let's identify the hypothesis and conclusion of this theorem statement. And this gives us the first and last lines of our proof. So we'll assume that these polynomials are different in Z3 bracket x. And our last step is the conclusion that their corresponding cosets are also different in the quotient ring. Now we also have this additional step. Because these two polynomials are unequal to each other, their difference, right here, must be non-zero. That's going to be useful later in our proof, so I just wanted to put that up front. To help us think about how to proceed with this proof, let's take a look at the last line, our goal. Now we wish to show that these two cosets are not equal to each other. And one way of showing that is to show that the difference of their coset representatives is not contained in bracket x squared. So the second to last step in our proof is to conclude that the difference of these coset representatives is not contained in bracket x squared. And this is going to be the new goal for our proof. So we hope to show that this difference is not contained in bracket x squared. So let's proceed by contradiction. In other words, we will assume for contradiction that this difference is contained in bracket x squared. And then we'll derive some sort of a contradiction from that assumption. Now, because this difference is contained in bracket x squared, we can say that this difference is equal to x squared times q of x for some non-zero polynomial q of x. Now, how do we know that q of x must be a non-zero polynomial? Well, it's because this difference, as we showed earlier in the proof, is non-zero. And therefore, q of x must also be non-zero. So because both sides of this equation contain polynomials that are non-zero, we can compare their degrees. Now on the left-hand side, we're subtracting a pair of polynomials of degree at most 1, and so the difference also has degree 1 or 0. Whereas on the right-hand side, the degree of x squared times q of x is at least 2. But that can't happen if we're claiming that those two polynomials are equal to each other. They can't have different degrees. And that's our contradiction. And therefore, our assumption must have been false, namely this difference can't possibly be contained in bracket x squared, which is what we wanted to show in order to conclude that those two cosets are not equal to each other. And that's the end of our proof, and also the end of this lesson. So I will see you next time.